Hello, everyone, and welcome to a new and wonderful day talking about valence bond theory. So, last time we went ahead and extended the ideas of valence bond theory we built up for the hydrogen atom and hydrogen molecule to second row elements. So, this more or less showed how I can build any combination of uh, atomic orbitals to build up wave functions for either sigma or pi bonds. So today we're going to try and extend a little bit outside of that and figure out how I can start to put multiple of these wave functions together, either by building up uh, bond wave functions that are a combination of more than one kind of bond, or by possibly looking at how I can slowly build together my various atomic wave functions to build a true polyatomic molecule. So, in order to do with this, I want to start by talking about a system that isn't well described by a single wave function. So in order to describe a single bond, I actually need to bring in a combination of at least two wave functions. So a classic case of this is HCl. And it turns out this makes a certain amount of sense because HCl has a covalent bond. So it's going to have a nice sigma bond. But unlike before, where I had two of the same elements, this isn't going to be a bond that's evenly shared. So it's going to be a combination of a covalent bond with something else. So the covalent bond we can treat very similar to how I did looked at the bonds for hydrogen or chlorine. I figure out which two orbitals are going to be overlapping. In this case, the hydrogen 1s and the chlorine 2pz. Again, by convention, we're overlapping the pz orbital. Starts with the first electron on the hydrogen, second electron on the chlorine. We have non-ideality, so we also have to switch. And because we're building up intensity in the middle, we use the symmetric combination, which of course then means the spins have to be paired. So we have an anti-symmetric combination of the spins, so congratulations, I have a singlet molecule. This is exactly what we want to see. And so while this is a little bit odd in the fact that I'm no longer pairing two of the same orbitals on two of the same types of atoms, I can indeed mix and match when looking at valence bond theory. Nothing here is too surprising. But we won't run into a slight problem. I know that these two electrons are going to want to spend a little bit more time on the chlorine. So I need to add in a second type of wave function. I can also think of HCl as being a ionic molecule, where I have two electrons on the chlorine and no electrons on the hydrogens. So this orbital is empty, this orbital is doubly occupied. Congratulations, they're essentially disassociated. I have an ionic compound. Now, we can also build up a wave function for my ionic compound. So I've got one electron on the pz orbital, and it turns out I also have the second electron on the pz orbital. And then because of non-ideality, I mix these two together. Wait a minute, these are the same thing. And when we bring in the normalization factor, it turns out what I just did was I made an atomic orbital while using the molecular system, which is actually good because it tells us that we get back the atomic systems when using valence bond theory if I choose to occupy my electrons in such a fashion. But again, if they do occupy the same space, just like for a multi-electron atom, that means the spins have to be opposed, so we still see this anti-symmetric spin. So I now have a wave function for the covalent bond, and I have a wave function for the ionic bond. Now what I can do is when I'm looking at HCl, I can say, wait a minute, HCl is a covalent bond with a little bit more of the electron density localized in the chlorine. So I have a covalent bond with a little bit of ionic character. So nothing stopping us from using our old friend, the superposition. I mix my two wave functions together. So by convention, I'm just going to give my C1 on the covalent as 1, and then my coefficient on the ionic as lambda. So notice this is not a normalized wave function. If you want to try and figure out the exact probabilities on each molecule, using finding the normalization coefficient can be very useful, but it's a little bit awkward for this case. And we'll talk about why a little bit more in molecular orbital theory. But for now, we can use a simpler trick because I know that the square of lambda is going to be proportional to the ionic contribution of the wave function. So if I've got my two coefficients squared, I'll still have the right ratio. So it turns out that 1 squared is 1, and that lambda squared is going to be, well, whatever lambda squared is. So for example, if lambda was 0.1, I'd have 1 squared versus zero point 0.1 squared, which is 0.01. And what this means is I'd have a 100-to-1 ratio of covalent character to ionic character. So this means that I would have roughly 1% ionic contribution with a lambda of 0.1. So your book goes into this a little bit more detail. Let me know if you need any help. But this is the general idea that just like we did before, the square of the coefficients will tell me a lot about how much of each character I have. And what you can do is try and figure out what value of lambda will minimize the energy of this bond, and that's likely the true state. So we'll talk again more about this idea of the variational principle a little bit more later. Right now, we're just trying to set the basics. Now, this technique of superposition can also be used for any sort of system that suffers from resonance. So if I have a organic structure, because this always happens in organic, where resonance is the answer, it turns out that we can build a total wave function out of all of the possible contributing wave functions. So let's make this a little bit more visual. Our classic case of resonance is benzene. So it has one potential structure with a corresponding wave function of psi1, and it has a second structure where I switch where my double bonds are of psi2. Now, it turns out that neither one of these is the true wave function. The true wave function is an even combination of both of them. So half the time I'm in psi1, half the time I'm in psi2. This is the ideas we brought up in general chemistry. But the real rub that quantum mechanics gives us is it's that I'm half of each one of these all the time and simultaneously, because quantum mechanics is great. And really what it is telling you is that you are going to be in a mix of the two molecular orbital states at any given time. You might be able to isolate any given one at any point in time, but as a net whole, you're going to be an even mixture of both. And this is something important to think about when you're looking at resonance structures in organic chemistry. You really do have both of these states at the same time, even if it's hard to draw it that way. And this idea even applies to cases where I don't have even mixtures, but instead maybe 2/3 and 1/3, where you have to change your coefficients accordingly. So before we finish today, I want to go ahead and extend valence bond theory to a very straightforward and important idea. It's about time we actually build up those polyatomic molecules like benzene. And in order to do this, what we're going to be doing is starting with a simple molecule, water. So the major idea is what we've done before. You're going to focus in on all of the partially occupied orbitals. So for water, it's going to, by convention, have a full S shell, and it's going to have a full 2pz. And I'm going to have a single electron in both the px and the py orbital. And hydrogen, of course, also has a partially filled 1s orbitals. So my bonds are going to come from the overlap of the px with the 1s and the pz, or the py, with the 1s. So this gives me two sigma bonds because they are direct overlaps. And that's water. It's two lone pairs, fully filled orbital shells, and two bonds made from overlapping valence shells. The unfortunate failure of valence bond theory stems from the fact that it gets the angles all wrong. So according to this, my y and x orbitals should, by convention, have a 90-degree angle because they're in an orthogonal space. It turns out that they actually have an angle of 105, which means we did something wrong. Now, I know there shouldn't be any problem with hydrogen because there's not a lot hydrogen can do. This means that our oxygen orbitals are wrong. So next time, we're going to try and focus on a way of modifying our oxygen orbitals to more correctly produce the shapes that we actually see in real spectroscopic experiments. So in order to do this, we're going to introduce hybridization. Take care. See you next time. Stay safe.